Hello, welcome to Project Euler number 6. Let's have a look at the question for this one. So it says here, the sum of the squares of the first 10 natural numbers is 385, and the square of the sum of the first 10 natural numbers is 3025, and you can take the difference between them and it's 2640, and then it's asking us to do that for the first 100 natural numbers. So I think this actually sounds like a reasonably easy problem, so I'm going to try and kind of show you two different ways of doing it. First, we'll do the way where we just do it like the sort of programming way with loops and such, and the second way will be, I think it's more interesting, it'll be sort of a more algebraic way of doing it, using maths, I guess. So yeah, let's go ahead and do the programming way first. So we need both the sum of the squares and the square of the sums. To get the square of the sum, we will first need the sum. So I can just say that the sum is equal to 1 to 100 dot sum. Helps if you has the equal sign. And then we're going to want to square that, so this is probably completely unnecessary, but we're going to define a function called square. Guess what it does? Guess what this is going to do? It's going to square it. And yeah, this is probably a bit pointless. I could have just inlined it, but there we go. And then and then we can just say, well, we want the squared sum. So squared sum is going to be equal to the square of the sum. Great. Next we want the sum of the squares, so sum of squares, and this again is just going to be kind of similar. We're going to go again 1 to 100, except this time we want to square them first, so we can do that with .map, and then we want to sum them, and we're finally going to get an answer of oh no, my lovely timer thing will just give us the answer out, so we can do the squared sum minus the sum of the squares. And I think it's quite interesting to think about, which one's going to be biggest just based on, without doing any calculation. And to me, I think the squared sum is kind of obviously bigger because you can think of it as you have 1 at the top of the triangle, then you have 2 and you've added that on, then you have 3 and you've added that on. So you end up with a triangle if you're just doing a sum, but if you're then squaring that, you end up with a kind of 4-dimensional objects because it's 2 dimensions squared. Bit hand wavy, I know. Whereas with the sum of the squares, you can imagine stacking these squares on top of each other, so you have 1 and then 4 underneath it, and then 9 underneath that, and 16 underneath that, and so on. And it's kind of like a pyramid, which is a 3-dimensional object. So the squared sum is pretty much always going to be bigger, and we'll actually see that this is definitely true when we do the algebra later. So why don't we just run this and see what happens? Yeah, I'm still always surprised by how slow these basic calculations take, but let's see if that answer's correct, shall we? I've just typed in the confirmation code. Check. Yay, how about that? So we've got the right answer. But let's see if we can get it in a more sort of interesting way, I guess. And for that, I guess I'll just use IntelliJ as a chalkboard. There's probably some proper chalkboard and stuff out there, but eh. Now we'll get to see how bad my sort of pen drawing skills are. But we want the sum first. Gosh, I really can't write, but we're going to go with it. And we'll just generalise this, and instead of summing all the way up to 100, we'll just sum it up to n. So we want to start at little n equals 1, and we're just summing our n's, and we want to think of what is this in terms of capital N? Can we think of a formula for that? So it turns out that little Carl Gauss, when he was a little kid, basically did this, because his teacher sort of told him in school, oh, just add up the numbers from 1 to 100, and he just immediately says, oh, it's 5050. And apparently the way he got to that is he imagined writing out all of the numbers in 2 rows. So one that's 1, 2, 3, blah blah blah, dot dot. I can't draw. There we go, little dots like this. N minus 1, well, it should really be capital N, shouldn't it? And pretend it's capital N, all the way up to, there we go. Let's make this into a capital N. There's probably an eraser, isn't there? Can you tell I've not done this before? So we're going all the way up to n, and then what you did is you just wrote the numbers in reverse order underneath it. So n minus 1, I guess you'd have n minus 2 here, and then you'd go from all the way to 2, and then 1. And then what he did was he thought about the sort of sum of each pair, and this turns out to be n plus 1. So 1 plus n plus 1 is n plus 1, and 2 plus n minus 1 is n plus 1. You can see where I'm going with this. So each pair adds up to n plus 1, and there are, in total, n pairs, because it goes all the way up to n. And because we're sort of counting twice, we're counting all of the pairs, we want to divide by 2 for the final result. So the sum is therefore going to be equal to 1/2 times by n times by n plus 1. So that's a great thing. So now I'm just going to sort of start erasing stuff. Alright, so it just copies the result up here on the left, and of course what we're actually interested in is what is the square of the sum. So if we just square both sides, that's obviously just going to give us a quarter n squared n plus 1 all squared, which I won't write out explicitly, but we'll remember that for next time. So what we then need to do is we want to, instead of thinking about the sum of n, of just numbers, we want to think about the sum of squares. So this result here, what's this going to be equal to? And again, we want it as a function of n, so we can do the subtraction right at the end, just plug in capital N equals 100, and let's think about how we can do this. So we're actually going to be computing this in using a bit of a trick, shall we say. So we're actually going to use what's called a telescoping sum for that, and we'll see why it's called telescoping very shortly, but we're essentially just going to consider the sum of n cubed minus n minus 1 all cubed from n equals 1 to what have you, to capital N. And what we'll see as we sort of calculate this is we're going to end up with like 1 cubed, oh my gosh, minus, I'm really bad at drawing, minus 0 cubed, and then we're going to end up with 2 cubed minus 1 cubed, and we're going to end up with, of course, 3 cubed minus 2 cubed. You can probably see where this is going, and the last term in this will, of course, be n cubed well, let's do the last two terms, actually. So you'll end up, of course, with n minus 1 cubed minus n minus 2 all cubed, and finally, the final term in this sort of series, I guess, is going to be n cubed minus n minus 1 cubed, like this. And you'll have to ignore my rubbish drawing. I've not really done this sort of thing before, but there we go. And we can see that this is telescoping because essentially what happens is, if I use a different colour, actually, red, is that that'll cancel with that, that'll cancel with that, this one cancels with this one, and what we end up with actually is just n cubed. I know that's like a squiggle, but it means cubed, is n cubed minus 0. So this thing that I guess I'm just going to call it, what should we call it, like Q? I don't know, I like calling stuff Q. We can say that Q equals n cubes just from this kind of telescoping that goes on where they kind of, all the terms like just cancel each other out, which is really cool. And then what we're going to do is we're going to think, well, what else is Q equal to? So we're just going to focus on this this sort of n cubed minus n minus 1 all cubes term. And if we just expand this out, we're going to end up with, I'll draw a little equal sign there, we're going to end up with n cubed minus, and I always forget my signs, I always get them mixed up, but from the binomial theorem, I guess, if you want to give it its fancy name, you'll end up with this sort of thing, and that's going to be a plus because they swap sign. And I guess just look at the binomial theorem if you don't know like how I've got to this result. And what's going to happen here is, as usual, we're going to get sort of, these guys are going to cancel each other out, and we'll just be left with 3n squared, and let's get this right, so minuses cancel, minus 3n plus 1, and I think I might have to start erasing some stuff, and because I'm kind of running out of space here. But essentially, this q is now also equal to the sum from n equals 1 to capital N of this stuff here, this 3n squared minus 3n plus 1. And you'll notice that this contains the thing that we want, this 3n squared. So we're just going to do a little bit of rearranging, and hopefully that'll get us the answer. Alright, so I just copy the stuff into the top left, and the sort of target quantity I guess we're looking for is of course this, I'm just going to call it S, the sum of squares thing, n equals 1 to capital N. And what we can see from our equation here is that we've got our n cubed is, we can kind of distribute the sum over all the different terms. So it's of course going to be 3s minus 3 times the sum of numbers, and we actually have a formula for that, so the next line is just going to be, let's just use that formula, and then we're also going to add on the sum of, like, from n equals 1 to n of 1. And this term's quite important because, like, you're summing 1 n times, so that of course is just equal to n. So the next line of this equation is just going to be n cubed is equal to 3s minus yep, see, nearly made a mistake there. That's a 3, believe it or not. No, we can draw a better 3 than that, can't we? 3 over 2 times by n n plus 1, like this. Lovely. And then we're also just going to add on this this n here from this last term. Great. So we can rearrange this in terms of s. So I guess, or 3s, because, you know, I'm not quite clever enough to do all of it in my head. So 3s is going to be equal to n cubed plus 3 over 2 n plus 1, and gets its own bracket now. N plus 1, and then of course, because we're changing over to the other side, that's going to be a minus n. Great. And then we can actually take out a factor of, I think, n over 2, I guess. So 3s equals, yeah, let's take out a factor of n over 2, like this. And what we're going to have inside is, I guess, n squared, like this, plus 3n plus 3, yes. No, because it's going to be 2n cubed, right? Because you're taking a factor of n over 2. Yep. Yeah. And then 3n plus 3, and then finally minus 2n, like that, which is fabulous. And then finally we can say n over 2, writing it really small down here, sorry. We're going to have 2n squared plus n plus 3. Fantastic. I got that wrong. Man. Actually, I've got that a bit wrong, so let's go back a few steps and correct it. So we're taking out a factor of 2n, so this term here should really just be minus 2, because we've taken out a factor of 2n, which then means that we go to n over 2, and then 2n squared plus 3n plus 1. Yeah, that looks right, doesn't it? And then for those of you who are, like, really good at factorising quadratics, you can probably spot that this will actually factorise into 2n plus 1 and n plus 1. I guess just work through doing the expansion in your head, and then what this finally gives us is that s equals 1 over 6, so I'm just dividing by 3 on both sides, times by n plus 1 times by 2n plus 1. And I actually have this, like, burnt into my memory from doing A-level maths at some point, but I guess not everyone does. So now that we've got this formula and the formula for the sum of numbers right here, we can actually use both of these to sort of algebraically work out the answer. Alright, so I've just written down like what we've established so far. So this is the answer, this sort of crazy looking formula. I just thought it was worth noting that it turns out I was kind of right about this first term being kind of four-dimensional. You can see it's an order 4 polynomial, and this term kind of being cubic or third order because it's an order 3 polynomial. So that was an interesting. I'm glad I got that bit of intuition right actually. So I guess we can either just like plug this into some code, set n equal to 100, and see if it gets us the right answer, or we can maybe factorize it. I'm pretty bored, so I'm going to factorize it. Actually, on second thoughts, it's probably not that interesting factorising it, is it? Do it if you want, but I'm not going to. So let's just plug it in and check the answer actually works, I guess. Alright, well, I guess we can just pretty much just write down the answer in one line, can't we? So, well, yeah. Val answer, well, no. Yeah, def answer with n as a parameter, and we're literally just going to use this formula that we've just derived. So it is n times by n times by n plus 1 times by n plus 1, all divided by 4. That's always divisible by 4. I will leave you to determine why that is. And similarly, this sort of quantity here is also always divisible by 6. And again, I'm just gonna leave it to you to figure out why that is. And then there's our formula. So we'll just get the answer by literally just doing answer of 100. And I really hope this is right, but let's find out. I think that's a different number. I forgot to divide by 6. Whoops. Let's try again. Well, I think that's right, but let's just double check. Let's see. I literally can't remember what the number was from the first bit. Yeah, it's right. Okay, great. Yeah, so I think this explanation of the whole telescoping something took way longer than I thought it would actually. So that's why this video is so long. So apologies for that. And like I think for me personally, like I actually prefer the first answer. I think it's a lot clearer in terms of like translating the problem from like the problem statement that involves that literally just involves sums and squares and stuff. Whereas this one I think kind of is an extra layer of abstraction. So for me, it actually makes it a bit more complicated, even if it does run a bit faster. So like I guess if you weren't doing 100 but a ridiculously big number, you'd probably use this one. But like I think for clarity of explanation, I do think the original one that I did was much easier. Anyway, thank you for watching. If you did watch it, and a special thanks if you got to the end of this rather long one. And I will see you next time. Thanks.